In our previous unit of study, we were largely investigating work, and we defined work in two ways. Mathematically, we said work is this a scalar quantity that's found by taking the dot product of two vectors, namely force and displacement. If the displacement isn't constant, then we have to integrate f dot ds. Our other definition of work is that it's equal to a change in energy. Let's clean up that definition a little bit and say that work is done anytime energy changes or is converted from one form to another. So that begs the question, what are the different forms of energy that we want to investigate? So I want you to think of all the possible forms of energy as being contained in this big box. We're going to say we can classify energy into two major forms. Energy that's able to be harnessed. So we'll call that, we'll give it a few names. We'll say the energy can be useful, harnessable, or the term we like to use is mechanical. Or energy can be wasted, degraded. Generally, anytime useful energy is converted into thermal energy, it's very difficult to harness it to do anything useful again. So our real point of emphasis is to study mechanical energy. Now, mechanical energy can also be subdivided into a few different forms. We'll say the two major categories for mechanical energy are energy of motion or stored energy. So the term we give to energy of motion, as you know, is kinetic energy. An object's kinetic energy is equal to 1/2 times its mass times speed squared. Okay, stored energy we refer to as potential energy. Think of something that you lift high above the ground. As soon as you release it, it converts its energy into energy of motion. We say an object lifted above the ground has the potential to be set into motion. The same thing could be said for compressing something against a spring. If you push something against a loaded spring and suddenly let it go, it has the potential to be set into motion. Well, potential energy can be divided into a few different forms. Let's see. We'll study gravitational potential energy. So anytime you lift something up high above a reference point, as soon as you release it, the force of gravity is going to do work to convert that potential energy into kinetic energy. When a compressed spring is released, elastic potential energy can be converted into kinetic energy. And there's other forms of potential energy. There's stored electrical energy, chemical potential energy. I'll just write etc. And again, we're going to mainly focus on just a couple of these. In this chapter, we'll mostly study potential energy if it's in the form of gravitational or elastic. And we'll wait till we get to Physics 4b to investigate electrical potential energy, and probably Physics 4c, the third semester of the course, to study chemical potential energy. Okay, so what we want are some equations to calculate potential energy. We know the symbol for kinetic energy is capital K. The symbol for potential energy is a capital U. So in other words, gravitational potential energy might be symbolized as U subscript G. Elastic potential energy, U subscript S. We'll derive these equations, but I don't mind giving them to you now. An object's gravitational potential energy just depends on three quantities: how massive the object is, the strength of the gravitational field on Earth, that's just a constant, always equal to 9.8 newtons per kilogram, and then the change in the vertical position. Or if we want, we can call it mgh. Elastic potential energy, we can derive this based off of Hooke's law. So in our study of elastic potential energy, we're going to restrict ourselves to the study of objects that behave as ideal springs. So elastic potential energy is equal to 1/2 K times the elongation or compression of the spring squared. All right. Thermal energy, the symbol we give to this, the wasted energy, we'll call it capital Q. In most cases, we won't have a formula to calculate it unless it was thermal energy produced by force of friction. Then the Q value is simply equal to work done by friction, which would be equal to force of friction times displacement, which would be mu times normal force times displacement. But that's just one example. The Q value could also be a result of non-conservative forces like air resistance or fluid drag. And in that case, it's much more difficult to calculate the Q value. So in most cases, we won't actually make calculations of Q. We'll just recognize that anytime energy is converted from kinetic to potential, it has the ability to be converted from potential back into kinetic. And energy can continue to be transformed back and forth from kinetic to potential. And as it does so, the energy is continuously harnessable. The problem is if energy is converted this way. When mechanical energy appears as thermal energy, that's it. It doesn't come back again. In other words, if we suggest an arrow going this way, put a big cross to that, it doesn't happen, right? Thermal energy is wasted energy that can't be harnessed once again. This all leads to the law of conservation of energy. But I'm getting ahead of myself. So for now, thanks for watching.